Thank you. Okay. So I talk about some story which I tried to start on some paper quite a long time ago, maybe 10 years ago. It somehow didn't follow. Yeah, so nobody paid any attention with it. Yeah, but I think the story is still interesting, and there are some new developments. I will explain what's going on. First of all, just recall you this idea of Alan Weinstein. The idea is that if you consider symplectic manifolds, they should form a symmetric monoidal category. Just denote tensor category, symmetric monoidal category. With the tensor product of, if you get two manifolds, you can take usual product of two symplectic manifolds, that will be tensor product, and what will be home from x1, omega 1, and x2, omega 2. It will be set of Lagrangian correspondences. But L should sit on x1, product of x1, x2, but in x1 you change the sign of the symplectic form. And you try to compose such things as correspondences, and you get, in general, troubles because of transversality issues. People now are trying to work it out in a certain thing, but morally it's a tensor category, and why it should be, because one can try to think about quantization. One can try to think that symplectic manifold loosely should give a complex Hilbert space, projective space. On this level procedure, say Hilbert space, which will be something like function on half of variables. And product of manifolds will be the things, and Lagrangian submanifold will gives a vector in Hilbert space. And if you go x2 minus, if you change omega, you should go to dual vector space. H. You should get H dual, which is the same as complex conjugate. Yeah, so it's kind of rough approximation of infinite dimensional linear algebra. Okay, now we have, these days we have a different quantization. Namely, symplectic manifold we can associate its Foucault category. It's an A infinity category. And the same goes from tensor product of goes to tensor product of categories. If you go to minus omega, you get dual opposite category, and such things Lagrangian manifold should give objects. This should give functors. So kind of Lagrangian correspondences gives functors. Okay. Yeah, so there are kind of two different quantizations, and they are really different. In the sense, here we put a purely imaginary Planck constant, and here we get real Planck constant. And they're kind of really different gadgets. Okay, and now, if we have tensor category, we can speak about various algebraic structures, like commutative associative algebra. And kind of slogan of my lecture is that integrable system. It means that you fiber your symplectic manifold of some base plus a Lagrangian section S is the same as commutative associative algebra in Weinstein category. Okay, what is associative algebra in tensor category? You have a map from unit object to A, unit object is point, and you get multiplication, unit, multiplication, and satisfying some axioms, yeah, commutativity, associativity. Unit is given by a section, it's Lagrangian section. And what is the multiplication? It's xv. Multiplication is given by a Lagrangian manifold in the product of 3 copies of x, but 2 with opposite symplectic form, and 1 is the original one. We get Lagrangian manifold, which is given by the following. We consider 3 points such that they lie in the same fiber of the integral system. So, set it first projection of these points are the same. This is some point B, and then x1 plus x2 is equal to x3 in kind of torus pi minus 1 of B. With the, in general integral system, the fiber is a torus, but because we choose a section, it has distinguished 0, so we can have addition law. So according to this addition law. So you get, and conversely, if you think about how to get commutative associative algebra in Weinstein category, you unavoidably go to integral system with some kind of, in general, we don't ask the fibers to be a tori, we want the fiber to be Lagrangian variety and abelian groups. Commutative, with commutative associative law on the fiber gives commutative associative law in this category. Now we can apply this to quantization functors, like Hilbert spaces, and then in this picture one gets something like algebra, commutative algebra of operators in infinite dimensional space. I will return to it later. And for the case of Foucault category, when apply this integral system, when apply this functor to integral system, you get a commutative algebra, commutative associative algebra in kind of category, in tensor category of infinity categories. And I claim this is algebraic geometry. It's kind of a notion of space. We have a category of shifts and we have tensor product. It is commutative associative. It's kind of maybe derived, but still commutative algebraic geometry. And in this way, Foucault category will be identified with category of, let's say, derived category of coherent shifts on some commutative space. Yeah, so that's a real integral system gives by mirror symmetry this commutative space. Yeah, in fact, there is a little more here because one can try to see what happens if one have commutative associative algebra in one state category. One have not only unit but something like co-unit, because Lagrangian manifold we can interpret as morphism in different ways. There's also kind of transposition. You get automatically, you get more. You get a co-unit, kind of trace from A to 1. And this co-unit, and this it will be actually Frobenius algebra. It will be such that if you consider varying on A, given by first multiplication, and then by the trace, then it's non-degenerate. And non-degenerate, it's purely categorical notion. One have kind of inverse, which is from A1 to A equals A. And when I consider something like inverse, consider such composition, it will be equal to identity of E. Yeah, so it's, you get automatically something more, and which, if, for example, applies this functor of Foucault category, will say you that its category is rigid. Every object has dual object. And this, for example, this pairing or co-pairing is given by pair of points x1, x2, and xx. With the same sign, so that x1 plus x2 is equal to 0 in fiber. Okay, so it's up to now it's all pretty clear. Now, so the goal of my talk to explain analog, what will be kind of natural analog of all this picture in algebraic situation, and then characteristic is positive. So actually from now on, I assume that X is cotangent bundle to some manifold M. I will consider other examples, kind of basic example of integrable system is Hitchin system with all various versions, when M will be something like moduli space of some rank R bundles on some curve C, and cotangent bundles with Higgs bundles, and it maps to B, which is a set of spectral curves. The curves in cotangent bundle which kind of projects to C this R4 cover. Because Higgs bundle one can consider as spectral curves plus line bundles generically. And if we get line bundle, we get spectral curve. So get such thing. And in this situation, what will be this quantization functor? How we go from symplectic manifolds which are cotangent bundle to something kind of linear like vector space or additive category. And in fact, if I try to think that, if consider, let's say, complex symplectic manifold, and try to define what is Foucault category of this complex symplectic manifold, it should be something, it should be this right definition the same as, let's say, D modules. Okay. So the quantization is category of D modules. And it's kind of too big category. If you consider analog of kind of small Foucault category, it should be maybe holonomic D modules. Yes. Now imagine that we have a apply the same philosophy as before to this quantization. We conclude the structure of integrable system should give certain remarkable, not a Lagrangian manifold, but a D module on a cube of M. The holonomic D module on M cube. And this D module will be this kind of multiplication kernel from the title of my talk. because this holonomic model can be thought it's kind of algebraization of notion of some nice function, nice equations. I will show you the examples of this module. Why such thing should exist and should be calculated? It follows from geometric length correspondence. Because this geometric length correspondence says something like this. It says that D modules, not necessarily holonomic, on M, this category, this derived category should be equivalent to some quasi-coherent sheaf on some another variety N. And in real life, N is what people denote something like band J, where J is reductive group of some curve or the space of bundles. And this will be, they denote it's log cis, but it's kind of J dual. You consider bundles with on curve with connection. Yeah, so the space has twice dimensions in N. So that's a story. And here one can put maybe cube as well. And here, for example, here contained of triple diagonal. And this guy should go to this multiplication kernel.
Cube is your suggestion.
Yes, for multiplication. One can go to square it, just to this pairing. Yeah. Or another way one can say that this category it has some tensor product because it's commutative situation. So it means it gives a tensor product of D modules without cube, and this should be given by some kernel. And this is this multiplication kernel. Yeah. So this multiplication kernel gives. Give structure of tensor category on holonomic DM modules. Yeah, so that's that's a kernel, and one can produce. Few stupid examples and two non-stupid examples. So kind of obvious examples. Obvious examples are the following. If M is any variety and you consider a holonomic denominator of O cube, the module will be kind of delta function of diagonal. Modular associated direct image sheaf on diagonal. Then we get just usual tensor product, pointwise tensor product of the modules. So that's one example. Second example, when M is a group, commutative group scheme. Like a affine line, GA, or E1 minus 0, GM, or elliptic curve, or abelian variety. And the kernel is given by kind of delta function of the graph of a group law. Graph of group law. Then you get convolution, additive or multiplicative, whatever convolution for holonomic D-modules. Yeah, it's already kind of examples.
The diagonal in the triple product is not Lagrangian.
It's not Lagrangian, but manifold is T star. M is not symplectic at all. Yeah, you take conormal bundle to the yeah. Or actually, one can marry these two examples. One can consider family variety of fibers over some base, such as fibers are commutative group schemes. But it's not integrable system. There's no symplectic structure. And one can make a kind of group law depending on parameters. That's more general situation. And there is essentially not one kind of maybe two examples. Trivial example. M will be just a fine line. So it depends on. In fact, it's related to 4 points on P1. It's kind of the first non-trivial example of Hitchin system. We consider SL2 it's a tool, a local system with unipotent monodromies around 4 points or something like this. And in this case, it's kind of like a case. The moduli space is again one-dimensional. It's essentially the same curve. And then one should introduce certain polynomial of 3 variables, which kind of really tricky. Now there are ways to write it. That's kind of main discovery. As a subject, you can introduces polynomial and the kernel, multiplication kernel. Sorry?
S is the point.
S is a number. Yeah, it's something. Yeah, it all depends on the choice of S. And multiplication kernel is given by the following. It's you consider minus square root of p multiplied by dx dy, so it will be left d in variable z module and right variable x and y. Model on x and y, yeah, because strictly speaking, this changing of going from this involution, which is which I was careful when I spoke about symplectics story. It's kind of replace left and right modules. Now, so it's a kind of such expression, and it gives this commutative associative structure. Yeah. This is almost equal to some trivial example, because maybe I can consider some version of more trivial example. Suppose you have a G on which acts finite group H, or maybe it's by automorphism of the group G.
G is the group.
Group scheme. G is a group scheme, commutative group scheme. And then consider M will be G mod H. You kind of project your additional law to the quotient. And for example, if you consider elliptic curve, which is doubly covers projective line by involution, by antipodal involution, and this will be four ramification points. Then, if you consider this multiplication kernel, will get delta function of some hypersurface. And hypersurface is given by equation p equal to 0. Yeah, so that's the origin of this p equal to 0. Consider 3 points on this elliptic curve. This will be 0 of the addition.
Does it have to be a subgroup?
No. H is a non-commutative group acting on G.
Yes.
In principle, here it's involution.
Okay, say again.
Yeah. For example, how to produce this hypersurface? You get a hypersurface in the cube of a fine line equal to 0. And namely, you consider projective, kind of rationally, consider projective line as a quotient of elliptic curve by antipodal involution. Consider group law. You get a kind of two-dimensional surface in the cube of elliptic curve, projects down by all involution. You get a surface in P1 cube. And this is the equation of P, nothing else. Yeah. But this group law is slightly different. Instead of delta function, I take minus square root. I can take arbitrary power effect. Yeah. So, and it gives some kind of new, interesting this multiplication kernels. Yeah, no, it's and kind of it's really mystery. Up to now, nobody really calculated essentially any other examples explicitly. What is this multiplication in slightly more complicated cases?
What do you expect the section from being?
Sorry?
What do you expect the section to be like in the unit? So in the Higgs bundle example.
Yeah. For example, in Higgs bundle, you don't have a section usually, but you consider maybe several Higgs bundles. Take disjoint union, and then you get fiber will be not connected groups. Like consider JLN bundles. Consider JLN bundles for all possible degrees, not all degrees.
So you expect some non-unital categories?
Sorry?
You expect a symmetric.
Yeah, disjoint union will be direct sum in this. Yes, it will be maybe not connected examples of such.
So I think he's asking about the unit in your category.
Unit in my category point.
No, but I mean like, so there is no unit map in the commutative algebra called.
It's also corresponding to a section. Yeah.
Yeah, but.
Yeah. For example, consider Higgs bundle when get on a line bundle is trivial. If you don't keep it as a degree, we can ask him to do it. Yeah, so actually, what this geometrically enhanced correspondence? Okay. What geometrically enhanced correspondence says? Correspondence also implies the following. If you consider, because we get this equivalence of category, here you get kind of exotic tensor product, here usual tensor product. Consider functors from this category, as of this categories to vector spaces, preserving tensor product. Functors from holonomic modules and this tensor, kind of strange tensor product and convolution product to dB of vector spaces, which are tensor functors should be given by correspond to point on n. Points of some n, kind of local systems. And this should be given by expressions like this. If you get holonomic module, then I sort vector space by taking R gamma with compact support of E turn some kind of L lambda. L lambda is again holonomic D module lambda at point of n. It just seems corresponding to all point lambda in this correspondence. So it should be given by R, and these are called Hecke eigenships. And this, like example, this modulus space coincides with a curve. Yeah, so it will be pretty nice. And then the fact that this functor is tensor reduced to the following property. If you consider multiplication kernel and consider pullback of answer projection of this Hecke for any lambda, if you integrate over a certain parameter of this Hecke eigenships, you get 2 copies of the original Hecke eigenshift. So you get this nice rule. And here Hecke eigenshifts will be, because it will be kind of tautological situation, it will be local systems of rank 2 on P1 minus 4 points. And then we get this property, which I don't know how to understand algebraically. One can try to approach it from different viewpoints. We get some remarkable local system on the cube of my variety. Which is some double cover respective to some points. And now we take, for example, pick 2 points x and y on P1 minus 4 points. So we get P1, we get points 0, 1, yes, infinity. Now we pick 2 points x and y, arbitrary, for any point x and y. We do the following. If you restrict, if you consider this fixed x and y in this polynomial, it will be some quadratic polynomial in variable z. So it means that you get some 2 other points so it means that some algebraically produce some other points on P1 minus 4 points, and consider double cover of my things from here to these 2 points. Now consider my local system, any local system of rank 2, calculate H1 of this tensor product, and we get fiber of my local system here times fiber of my local system here. Yeah, it's some kind of remarkable coincidence of things which we can try to prove in different ways, maybe topologically, but already topologically it's pretty non-trivial because it's for all local systems, not for any one. It's kind of should be for identity for functions and model space of local systems. And also, the same thing should be true if you consider elliptic shifts, and maybe over finite field. And then I cannot see a clean strategy how to attack this problem. It's kind of pure topological identities that for any, let's say, elliptic shift of rank 2, you make this some calculation, take this 6. Yeah, so it's so it's pretty mysterious property. How one can prove it? Yeah, but it's definitely true by various means. And among this, there's something what one can try to extract from this story. Among this this bundles with connections, there are things called operas. That means that you write equation of second order as equation on scalar function of maybe high order, and then introduce to the following property for this kernel, for this multiplication kernel. Namely, let's introduce the following operator, H. One, this will be kind of commuting Hamiltonian. Namely, it will be differential operator d over dt it's some kind of formally self-adjoint operator in one variable. And then variable t. And then the following property holds from this kernel. It's kind of left and right modules for various things. If you apply operator h1 in z from the left, okay, it's the same as you apply the same operator in variable x on the right. The same is applied to the same operator over y on the right. Yeah, so and this kind of if you consider eigenvectors for this operator, whatever space of functions, then it will say that if you this k is, if you try to expand the sum of eigenvectors, with some eigenvectors with the same eigenvalue in three variables from all directions. It's kind of correspond to this property. And in general, if you consider this integral system, kind of quantized integral system in the sense that you get family of commuting Hamiltonians, you can write the same system of equations for commuting Hamiltonians. Unfortunately, the system equation is not it's underdeterminate. For example, here we get two equations for functions three variables. It's kind of 2/3 of all determinants, and the reason is the following. If you can try to think, it's clear that there should be many solutions of this equation, not to be very non-holonomic model, because for each eigenvalue you can choose, you can rescale the sum of three factors with the same eigenvalue. Yeah, so there's some ambiguity. No, yeah, I don't know. No, from this point you get undetermined system, and one should kind of extend it to some determined holonomic system. And in fact, we know what is this even characteristic variety. This semi-classical Lagrangian variety gives a group law. If you apply to kind of more complicated Hitchin system, and group will be semi-simple, there's no abelian part, then this Lagrangian variety will be normal bundle to some very complicated hypersurface in a cube of model bundles. And it's kind of the challenge is to interpret this hypersurface as a ramification locus of some family of varieties, and how to see its naturally point of singularities of this D-model. Yeah, so up to now, essentially there's no, it will be one more example, which is a bit simpler. I'll show you in a few moments. And that's it. Yeah. So people tried. Some people, not many people, tried to make a little variation. We consider again as a two, but put ramification not necessarily important around these parameters. Yeah, so it's kind of. I think that's the reason why this whole project didn't really start, because we really don't understand the formula of how to write it. Yeah, also it's kind of from pure theory you get over diagonal to something.
The time was the role of these Hamiltonians in the project.
No, Hamiltonians. For Hamiltonians it's a corollary because eigenvectors of common eigenvectors of Hamiltonians who gives you special this holonomic eigensheets, and for this special family it's reduced to some kind of elementary equation, but in general it's not clear what is it, but at least it's clear that it should be some canonical object because of this. Geometric Mendelssohn correspondence. And in general, let's assume that such thing exists in plentiful, yeah, so although there's no trivial examples, but I claim that such things can be thought as kind of generalizations of algebraic geometry. Yeah, so there are many reasons. For example, you get symmetric monoidal categories. You get them new bizarre symmetric monoidal categories. Or for example, consider xa1 and additive convolution. This can be thought as something, this parameterizing additive characters of your field. This eigenships, if you try to think, it will be exponent of something times things, and if you consider Jm and multiplicative convolution, it will be multiplicative characters. And then one can try to see, for example, what is gamma function. Gamma function, it's integral of product multiplicative characters and additive characters. So gamma function is a function of two variables. And can be thought as corresponding to the guy consider product of two such things. Yeah, so one can think about this. I think it's kind of generalized schemes, but let's say what, for example, we can say what are holonomic demodels, so kind of Motivic shifts will be by definition Motivic shifts on original guy, and this will be kind of Fourier transform identifying two different to the properties. And for example, there was some identity by Barnes. If you have if you integrate over appropriate contour, product of 4 copies of gamma function, you get some complicated something like this. Which can be thought as identity between some kind of transcendental stuff and such thing one can in a sense prove purely algebra geometrically. I'll explain you in a second how to formulate and prove. Things. Yeah, one can make a version of this whole story. Integral systems now will be over finite fields. Yeah, all the things, all complex numbers have analogs, and I'll explain in a moment. Yeah. So we start with again variety over Q. And now multiplication kernel will be some, let's say, elliptic shift on a cube of Yeah, in principle, the most optimal will be some Motivic shift, some kind of family of varieties, and from which we take Motivic shift. So we can again formulate the same axiomatics, and varieties multiplication kernel will be thought as kind of generalized algebraic variety. Now I want to explain you in this case of finite field, for example, what are points of this variety of the fixtures variety over again finite fields. The story is the following. Let's a bit kind of Motivic constructible shape. Again, it will be through this things like symmetric monoidal functor, like quantization functors. We consider category. We consider some tensor category. Objects are varieties over any field K. Any field K. Objects are varieties over field K, and home between one variety M1 and M2 M will be K0 of the category of Motivic shifts on the product. And yeah, so we'll consider kind of linearized version. One can consider better the whole category of shifts as a homes, but let's go first to K0. Then in the composition given by the following, you take two pullbacks, but when you take push forward, you consider push forward with compact support. And if K is a finite field, then this category, called category CK, admits a tensor functor to rational vector spaces. Namely, variety goes to rational vector space generated by a finite set of points. My variety of finite field, which is finite set. And if you get shift on a product, you calculate trace of Frobenius, you get matrix, rectangular matrix, and usual story goes as this composition, shift composition goes just multiplication of matrices. And in particular, if M is commutative associative algebra, like for this complicated kernel, then it implies that this thing is again commutative associative algebra over Q. And there is a simple mechanism which holds in all these examples which I know, which guarantees the algebra is semi-simple. I mean, in real life, what happens on M, usually on M we have some involution, sigma infinity, it's kind of Frobenius at infinity. Get an involution, and also we get a trace. A trace which will be non-degenerate trace. Inside that trace of AB star will give a positive definite form on the nose, namely if you get a shift, you get a function on M, it will be the sum of products, pointwise kind of diagonal matrix. Trace Frobenius points. x. Yeah, so to the automatically positive definite. Yeah, so get kind of, and in this case, this will be a commutative star algebra and defined of Q, so the sum of CM fields, complex multiplication fields. Oh, maybe I don't. Yeah. Yeah, yeah. Yeah, so no, I better don't want to concentrate. Yes, yeah. So what happens? You get, and then definition. If you get this Anderson multiplication kernel, you define what is the set of FQ points. It will be a set of homomorphism of this algebra over Q. Maybe I called it functor Q. Q bar. And if you consider an example like additive group or multiplicative group, we get exactly usual characters of finite groups. Sorry?
Why do you call them FQ points?
Because one can say it's, one can apply for any n. One get for each n, we get a larger set. You get kind of tower of finite sets for any n greater than 1. Again, kind of in naive examples, you consider like multiplicative if it's correspond to multiplicative convolution, it will be multiplicative characters of this field. They take values in Q bar. Sorry?
The category is not linear.
It's not linear. It's kind of category or rational numbers. Yeah. No, but these things can be thought as a variety. I claim that they have something like points. First of all, they have points, and in fact, there is a map from. Yeah, there's interesting things from how these things are embedded one to another. It's a non-trivial formula. For example, how you get this FQ points embeds to FQN points. You should make a homomorphism of algebras, yeah? So it means that we should get the homomorphism of algebra of FQN and M map in opposite way. And how to make homomorphism of algebras, you should for any point here and point, because it's the morphism of vector space with a basis, so it should be given by some matrix. Yeah, so it means that for each point B1 in M of FQN, and for any point B2 FQ, one should calculate some integer number. And how it goes? The story is the following. Multiplication kernel. I recall it was an element of constructible shifts or whatever on M square times M, and it was invariant under involution. I maybe call this multiplication of two elements. Then, because it's commutative for social algebra, one can multiply n elements. So for each n, one gets multiplication n, which is db n, which is invariant under Sn. So we should mod out by Sn. And because it's invariant, the story is the following. We kind of multiply point, or we can go to shifts. One can have shifts and one multiply shifts. One can have point B1, then apply Frobenius to B1, Frobenius to Frobenius. We get kind of cyclic orbit of Frobenius but now we twist here, because we twist here FQ structure using action of cyclic group. One can produce this from this equivalence. One produce the right thing here, and one get a map from this finite algebra, so embedding for the field. So we get kind of like usual picture of what are points of a variety of finite field. The only new thing that you get eventually kind of FQ bar points. And on the set of FQ bar points, you get action of Frobenius, generator of Frobenius, but also action of the Galois group of CM cover, closure of Q. And the Galois group contains central element complex conjugation, which was a sigma infinity. Yeah. So you get kind of a mixture of both finite fields and positive and zero characteristic. Sorry, but the rest is the following. And one can say, for example, we just declare what are Motivic shifts on this dual space as Motivic shifts on original space. But when I calculate these eigenvalues, you apply this kind of Fourier transform, and then at each point on the dual space you get kind of eigenvalues of Frobenius here. Yeah, there is a kind of really mysterious story here. If you start with any constructible shifts, its dimensions kind of bounded everywhere, and in particular get it uniformly bounded how many eigenvalues sit at every point. And it looks that for these Fourier transforms, you also get uniform bounds, which is pretty tricky property. Sorry? No, there's no bad ones. I don't. Yeah. So there is this language, and what is remarkable also, you see that this geometrical Lagrange correspondence was developed kind of. There were two things by kind of Greenfield. He first made actual Lagrange correspondence for functional fields, then a geometric Lagrange correspondence. But the things are kind of don't really talk to each other. They are not part of the same picture, and claims that really one can extract from the multiplication kernels all those Greenfield modular spaces. Just on the nose, let me try to formulate. By the way, just remove. There was this identity for gamma functions. One can do the same over finite field to get finitely many functions on multiple characters, make the same story to the same identity holds, and one can prove it because all calculation on this fake varieties, parameters for gamma functions, can be translated to calculation on usual varieties, and will be usual calculation with motifs, which would do part of Algebraic geometry. So now about kind of generalized Lagrange correspondence of a finite field. I propose the following thing. So suppose you get things with Motivic multiplication of a finite field. The examples were not very plentiful, but you have it. And now one can ask the following three levels of equations. We consider eigenshifts, define it over FQ. So it means that we get this L lambda, which is in Motivic shifts on M, maybe with coefficients in Q bar. And there's a property that multiplication, the same thing which I explained, multiplication by this Q bar of L lambda, and take is equal to L lambda. write this defining equation, it's kind of this complicated final object, kind of analog of Hecke eigenships, geometric finite field analog of Hecke eigenships. The second shift one can consider is more elementary. Is class in K0 of Motivic shifts on M, which gives a homomorphism on kind of numerical level. Homomorphism of rings kind of numerically, and something it will be really exactly this is what I defined the point of this thing, a homomorphism of algebra Q to multiplication to Q bar. Multiplication induced by the kernel to Q bar. Yeah, that's a finite set. And definitely one can forget about categorical structure, go to K0, but also go to just collocate trace Frobenius only points at FQ, not on other things. And the conjecture is that all things are identities. So it means that and in fact, one there is a simple formula how to get back from homomorphism of M Q bar to get eigenshift. The idea is the following. There are finitely many these eigenshifts defined over Q. Let's take their direct sum. It's still some kind of complicated Motivic shift. And I should just define this shift and define the action of the algebra. Six of them one can check it with the Hecke eigenshift. I don't have really time to explain it in details, but yeah, in fact, one can really work with case of commutative group schemes. It still gives the formula which works universally. Yeah, for example, you have some let's say abelian variety. And you get addition. Now, we can see the various characters of this group. Bar. Characters, and they should give then should give some eigenshift, Hecke eigenshifts. Now consider points in F and M, F, Q, N. What will be the trace of Frobenius of this point, of this lambda? And it's easy to see that it's equal to x. And consider x plus Frobenius of x plus. Okay. Yeah. So that's a simple formula. And now we take sum of all lambda of all the things of all characters. We see the following. We get number of points of variety of FQ if the sum is equal to 0, or 0 if it's not equal to 0. Yeah, it's kind of complicated formula, but then one can write the following. It's number of point y and FQM such that x equal to y minus Frobenius of y. Yeah. If it's equal, if x can be expressed this way, that it means that this total sum is equal to 0, and number of choices is exactly these things. Otherwise, it's 0. Yeah. Yeah. So you can write this formula, and the same formula works in general for this general integral system. You consider in terms of algebras. Maybe I can tell you. So this sum of Hecke eigenshifts is the following. We get algebra, in whatever category we have, and Frobenius gives automorphism of this algebra, commutative algebra. And in general, we consider commutative algebra in symmetric rigid symmetric manual category in Frobenius. Then I get a functional. E on A goes to trace Frobenius composed with multiplication by A. Yeah. If we want to translate these things to shifts, you get what I claim direct sum of Hecke eigenshifts. That's exactly coincides with this definition. And the question why this algebra acts on this thing, the story is the following. If you consider elements of algebra which on this Hecke eigenshifts, the story is the following. It's trace of certain functor depending on parameter A. But if you consider A such that which is invariant under B, then B commute with this composition as functors. So you get two commuting functors. And then if you get two commuting functors, then each of them define end of functor of some category and have some kind of notional trace, like multiplication kernel you consider restricted diagonal, then each functor gives automorphism of the trace of another things. And in particular, you get these things which are invariant under Q acts on this object, and it looks that it goes numerically through this finite dimensional algebra, and then you get kind of way to approach Greenfield moduli. Yeah. Greenfield moduli in general are kind of complicated objects, is a kind of great inventions, and it's a kind of transcendental invention. And I claim if you know the kernel, you don't have to invent them. And particularly in this example, I can really write explicitly formula what is Greenfield moduli space. It's just substitute in this kernel x1, x2 equal to x1 to power q. Essentially, that's it. Yeah. Yes, that will be. That's it.
No questions.
Everything is clear.
Yeah.
Okay.
So at the beginning, you mentioned that if you start from this XYZ relations,
Yes,
you have
yes.
this commutative and the product structure.
Yeah.
It seems that it suggests that the converse may be true.
So converse.
Converse.
Yes, yes, yeah. Of course.
Are there any reasons that you expect so?
No. If you want this multiplication given by something geometric, not by abstract object of a category, then
Yeah, I understand.
yeah.
So-
Yeah.
okay.
More questions?
Yeah, I have a question. So you wrote some time ago the paper of the motive over finite fields.
Yes, yes.
So this is a progress with respect to the paper.
Yes, yes, no, essentially.
What's the new?
No, for example, this idea about how to get this universal sum of eigenshifts. It's not much progress, I have to say. This is.
Okay. Last chance. Okay.
Thanks again.